This article is a repost from my personal blog at https://marccgk github. I recently wrote about why I think object-oriented programming is not a good tool to write code. In that post I wrote, however, in my experience, is taken as fact standalone software development by the majority of professionals. Object-oriented programming is often taught and, therefore, learned right after the basic programming constructs, variables, conditionals, loops, basic types and, in languages like C, pointers and basic memory allocation deallocation. Hence, most people have only approached medium to large codebases from minor plans, although there are large codebases written in non-null languages, e.g. the Linux kernel, written in C. I'd argue most sizable codebases currently in development are built using object-oriented design, not an empirical study. Based on my experience working on C codebases, in this blog post I do like to present a different starting point to approach writing software. Obligatory caveat: this is not a one-size-fits-all solution. No, it does not pretend to be. Writing code is still a craft more than a science. So in my opinion, do this, do not do that. Advice should be paired with measurable pros and cons. Having said that, I should also note that as a community, software developers do not even agree on what characteristics make the list of advantages or disadvantages, or what priorities should be assigned to them. I assume you are familiar with my Acton's Data-Oriented Design CppCon 2014 talk. If not, go watch it now. I will wait. Data-Oriented Design (DOD) is a fundamental concept. Understanding how the hardware works at a high level is a prerequisite to writing instructions for a computer to execute. However, DOD does not tell you how to write code. In this conversation with Ericson that my captain made public, Costa explains why DOD is not a modeling approach. Q is not data-oriented design, just Dataflow programming. R, why DOD is not a modeling approach at all. I will quote an exchange with Costa Ericson's answer, with permission, on this subject. No, not Dataflow programming. Dataflow programming, as well as wood for that matter, is a modeling approach, and specifically for Dataflow programming, by expressing data connectivity as a graph. While neither me, nor my Acton, nor Noel, Llopis, has ever provided an official definition of DOD, nor have we really been interested in doing so, nor would we necessarily 100% agree on one. I would argue that DOD is not a modeling approach. In fact, it's the opposite thereof. As Mike has eloquently pointed out elsewhere, computation is a transformation of data from one form into another. DOD is a methodology, a just way of thinking, where we'll focus on streamlining that transformation by focusing on the input and output data, and making changes to the formats to make the transformation as light as possible. Here there are two definitions of light. Mike would probably say that light means efficient in terms of compute cycles. I would probably say light means in terms of code complexity. They are obviously related, connected. The truth might be in between. I say this is the opposite of a modeling approach, because modeling implies that you are abstracting or not dealing with the actual data. But in DOD, we do the opposite. We focus on the actual data to such a degree that we redefine its actual layout to serve the transformation. DOD is, in essence, anti-abstraction, and therefore not modeling. In practice, we find a balance between the anti-abstraction of pure DOD and code architecture component needs. I do not know. I think different people will find that different modeling approaches work better for them, and that is alright. Personally, I just like to keep things simple, really simple, and build complexity only when 100% warranted. I have seen only too many clean up, refactor, simplify, and address technical depth tasks to understand that complex solutions, in the name of some abstract goal, e.g., extensible, single responsibility principle, DRY, etc., do not work out in the end. So, what does simple mean to me? Simple means straightforward. Simple code is code that is easy to understand by itself. No knowledge of other code or foreign concepts needed. This immediately rules out most of the CSTL, like, this is not simple code, it's just a chart. But chart does not make it simple. To understand this two-line snippet you must be familiar with a lot of concepts, STD, vector, Marc complex standards, iterators, STL algorithms, templates, or generic metaprogramming, etc. On the other hand, this is a lot easier to understand. This last snippet only requires basic programming concepts to be completely understood: variables, pointers, loops, etc. There is only so much that can be done with simple loops and accumulating values, with growing amounts of features, and therefore code complexity will invariably materialize. However, striving for simplicity should always be on the front of your mind, fitting and shop and not giving into the path of least resistance. There are inherent complex problems, though, and they require complex solutions. One of such complex problems is extensibility. That is a way for the user to provide custom functionality to some software without modifying the source code. This problem justifies and necessitates a complex solution, e.g., a plugin architecture. As I said, this can adopt different forms for different people. I can only speak for myself, but what follows is what I have found to work for me, and what I have learned from other people that take a similar approach to code. Code is easier to understand when it's written linearly, in a procedural way, that generally takes the form of long functions that do one thing conceptually, but might be composed of multiple subtasks to accomplish the main one. These subtasks are not extracted into their own standalone functions, though, until there's a reason for it. That is, the code is already duplicated in 2 or 3 places and the commonality is large enough, i.e., 90%, that the cognitive overhead of another function is superseded by its usefulness. However, there's also room for small functions, in contrast with large functions that implement main features. Short functions tend to be helper functions that get called from the large ones and return immediately. Some examples of such functions are allocations, e.g., a temporary allocator might just but a pointer, make create functions, math libraries, e.g., vectors, matrices, etc. Physically separating the code like this has several advantages both for the programmer and the compiler. The purpose of all code is to transform data from one format to another, from Acton's 3 big lies. Therefore, you know what the result of the transformation looks like. Working from the final format backwards makes it easier to write the least amount of code to satisfy the transformation at every step. For example, if you were to write a software rasterizer, you might want to start by allocating pixel memory for your window and clearing to a single pixel color. Then, change some areas of the image to the color you want,
e.g.
the corners. Then rasterize rectangles that are 100% within image bounds. Later some rectangles that are not within bounds, clipping. After that, try rasterizing triangles, and only after rasterization in 2D works, start working on 3D geometry and projections, until you can load arbitrary 3D models and fully rasterize them. This method will ensure you only write the solution to your immediate problem. The code will change a lot, but it will change as the problem itself evolves. The patterns and algorithms will emerge from the solution and not from some preconceived notion of what the solution should be. Memory management tends to get a very bad rap of being too hard for mere mortals, and programmers are recommended to stay away from it. That's why one of the main features of high-level languages is automatic memory management by